for tonight? I wanted to start out by talking a little bit about the program that we have at College DuPage, and more importantly, how we're trying to impact the pedagogy of meteorological education across the country. And this is really what brought this event into being. It's part of an NSF grant that we've been working on, to try to figure out a good way to get information to schools, increase their education practices. And I'll tell you the motivation. And I think just talking with a lot of people here, it's really made a difference in what people know when they are at certain levels of their undergraduate education. And this is what this is all about. I feel that there are many, many programs, the majority of programs in the United States, when you're interested in becoming a meteorologist, they basically tell you this: well, we have one course, but meteorology is based on math and physics. Come back when you're ready. And I think that's really what it is. And unfortunately, meteorology is a science to itself. It uses math and physics to understand the atmosphere. The problem is with an attitude like that is that people tend to get discouraged fairly easily when they're going through the rigors of math and science to do something that they really care about. And obviously you saw some of the people here today, and I would guess I'm addressing most of the people here, are passionate about meteorology, primarily forecasting and severe weather. And that kind of passion needs to be encouraged, not shut down for 2 years while somebody waits around until they're a junior, and then you start taking all sorts of applied calculus in the courses, and you never really get an idea of what's going on. I think the goals of a quality program is, at least for me at a community college, and this would be true of the first 2 years, is I put it down to increase transferability, but I also want to prepare students for continuing education and to prepare for the workforce. It has often been felt by many meteorologists, Chuck Doswell as one of the strong spokesmen, is that people are getting out with their bachelor's degree, they can't forecast, and they can't do research. And I'm not really sure what that means about the programs when people are coming out of school and they're not really sure what they're going to do. And I think that's a problem that's inherent to the way the system is working, because you're missing out on the wealth of experience that you get for 4 years in a program, not just the last 2. So questions that I think need to be asked is, are third-year transfer students, or really I guess that would for any 4-year program, are third-year students really ready for the curriculum they're getting? Are they ready to get some of the calculus-based materials? And it seemed to me that as we went through some of this stuff in the last couple of days, there wasn't a great deal of high math that was being presented. There was a lot of information on radar. There was a lot of information on map analysis. There was a lot of information on forecasting, none of which needed the higher mathematics to understand. And yet, it seems to me that most people who are in junior year have a hard time understanding that because they've never seen it before. I was talking to some people from NIU who are doing some stuff in the using the thermodynamic diagrams. Let me ask you this. What year do you first get exposed to thermodynamic diagrams? How many freshmen? How many people get it when they're a freshman? Sophomore? Junior? Senior? How many people who are ready to graduate, maybe this May, don't really feel very comfortable using them? Is that true of anyone? Or are they doing a better job here? Yesterday I asked about radar interpretation. How are you at that? Were you good at it? When did you learn it? You guys from Colorado, how about it? How's your program there, Tony? Seriously, I mean, when do you start doing the thermodynamic diagrams?
Very briefly at the freshman level, but really not until synoptics junior level.
Okay. just to let you know, at the College of DuPage, we started out, we have 2 basic introductory courses. An intro to meteorology, which is the standard, and then we have a course called severe and unusual weather. And we spend about 5 or 6 weeks doing thermodynamic diagrams. And from my experience, and maybe this isn't true for everyone, but the class tends to be split, with half the people getting a clue and half the people never finding it. And it's bad, because we talk about lifting parcels, and there are people who after 5 weeks have no idea what that means. And these are pretty decent students. And I would really question exactly how much do you use them as a freshman and sophomore. Let me ask you one more question. How many people spend a lot of time in the weather lab at your school doing forecasting as a freshman or sophomore? What school are you guys from back there? What got you into the lab? And you guys, what do you guys have first? Do you think it helps you? And you guys from UNC Asheville? If that's a good thing. Did you guys do it as a freshman? Did you do it as freshmen? The rest of you, when did you start going into the lab? Junior year? Well, some of the rest of you were. Missouri, what's your program like?
They have a course in second semester. It's a weather briefing course. So that's for freshmen. So they are in the lab, and then we have a forecast contest that's optional that some of us do.
Okay. Where are some of the other schools? Ohio State, where are you guys? How do you guys do? When do you start? Those of you who, all of you with meteorology degrees, what was it like? What was your first experience like in the lab? Was it intimidating? Like you don't know anything. I've known that feeling several times with some of the people that spoke today. One of the things that we're working on too, and this is probably the other big point of emphasis, is that there is a plethora of data out there. There's information on the internet, more than you could possibly know. Unfortunately, I think as we saw today, we're getting way too investigated into the model output and the computer analysis, and nobody's doing hand analysis. How many people regularly forecast, meaning at least once a week you go in to do your own forecast? Raise your hand. How many of you use hand analysis? A lot. You guys who spoke today, and those of you professionals, is that enough?
Meteorological cancer. Serious.
Meteorological age.
Go ahead.
We need more unanalyzed base maps on the web. Yeah, right.
What was that?
We need more unanalyzed base maps. How many? We have, the only thing we have is we have the upper air charts on a white background. We need more of those.
Take the lines off.
How much detail do you want on a map? Like a surface map? Anybody have other opinions on that?
He's right.
Does anybody disagree that hand analysis is useless?
Just give me the option.
I mean, would you be willing to go up against everybody and argue a point for that? If that's the case, oh, somebody's. stuff we have are just the maps. So it's just that GIF image. On our page or on others? Oh, others, okay. Yeah, we're trying to separate also sounding with the written text so that you can print out just the written sounding and do your own plot. And you don't know where that is? Anybody know where that is on?
It's FSL.
FSL? I think these are great exercises. I mean, there's how many people have done composite maps, like Roger was talking about a little bit? Do you guys do them regularly, or just learning it in the class? Is it helped? I mean, I don't want to sound like a little Chuck Doswell puppet, but he made a point. You know, he pays me for this. You know, this whole meal was on Chuck. It's just an ego thing for him. I can't remember what I was going to say. Oh, one of the things that I think is really wonderful, and what Chuck says, and this is absolutely the truth, is doing these type of understanding the atmosphere when you do forecasting, is it forces you to understand the physical processes of what's happening. I mean, you have to understand what does it mean to have low-level moisture return. And in doing the hand analysis and doing the hand forecasting and getting dirty and taking blank maps and drawing up composite analysis, that's what helps you understand what's going on. Then when you take your class in dynamics or synoptic lab or whatever, and you're learning some of the math and you're learning the primitive equations, etc., you have a good physical understanding of what's going on. And I think that's the most motivating factor you can have. When a teacher starts talking about divergence, and you're taking the curl of velocity, and you're trying to understand vorticity, I think you need to have a physical conceptualization first. And I think the physical conceptualizations can be taught at the freshman and sophomore level. So that when you start taking the math and start applying it, you're like, I know what this is all about. And I just think that what I've seen across the country is people don't know what that's about until somewhere in their senior year. And by that point, they've lost 4 years of forecasting experience and really understanding the field. And that's why they're not coming out of school ready. And I think anybody who's in undergraduate education needs to address this issue. We're talking about throwing the data online. I think we need to look at how we're going to teach this. Because right now, and probably less in meteorology, but in most fields, when they do online courses that they call, it's what they call shovelware. It's what they have in their notes, and they shoveled it to the computer, and now they call it a course. And it doesn't teach anything. It just is information that's more readily accessible. And we need to figure out ways to get the information out to people so that they start using it. And maybe having more maps that are open are going to get people with their hands dirty. Yeah, Chuck?
Paul, I can't emphasize enough how important storm chasing can be as an educational tool. I think that the really neat thing about what you've done at COD is to get your people involved just that way. Storm chasing can be terribly dangerous to your academic career, but it can also be the key to your success as a meteorologist. You got to learn how to walk that tightrope, but forecasting for storm chasing has this incredible feedback about reality that you never get from textbooks.
Kind of ironic, you walk into 9 or 10 of the best offices in the Midwest, and what do you think the best forecasters in that office are?
Chasers.
Yep.
Chasers. We have an undergraduate class in storm chasing at COD. We actually offer credit. And, well, just raise your hand if you've taken that course. Okay? Going to. It's a phenomenal thing to do because, first of all, we take a prerequisite of Earth Science 150, severe and unusual weather. So people have some clue. We go through an extensive spotter training. We do radar unit, and we do thermodynamic analysis. Then when they come into the course, we do case studies and we do different topics every year. We go out chasing, we take all the data online, we do as much analysis and forecasting and daily weather discussions as we can, and then we'll go out there and look at the storms and see what happened, and then do a post-mortem on it. An example is Jeff Milo, who is he's my student aide, and 2 years ago, Jeff went chasing for the first time, and he was just starting to understand this stuff. He looked at us doing maps and forecasting. Finally, he's figured out what's going on, and there was a time last year we were sitting in eastern Oklahoma on, what was it, May? I'm not the date guy. On Memorial Day, the day before Gerald, in eastern Oklahoma, and we're sitting and waiting, and you know, it's getting 6 o'clock and nothing's going on yet, and I'm getting really scared, and I was about to call Roger down on SPC, and Milo's back at the weather lab going, no, just wait. There's a jet coming through, you can see it with the cirrus streak. Once that area comes over the dry line, and you know, you're going to destabilize the atmosphere and it's just going to go crazy. I'm like, oh Jeff, no, I don't know if I trust you, you're just a kid. So he's like, no, man. And you know, Jeff's got hair down to somewhere around Paducah. And I can just see him back at the lab not knowing what's going on, but he's going, no, trust me. So sure enough, we see some cirrus out to the southwest, and we're like, okay, well, we'll just wait it out. And within half an hour, huge supercells all over. We ended up getting 3 tornadoes that day, and it was just a phenomenal experience. And Jeff's, when we went back, he's like, you know, I just get it. I get it. Jeff, how are you at math? Now, if I could just somehow do a math conference and get him motivated to do something fun. Anyway, the way I look at it is forecasting here, it serves as a foundation to the fundamental concepts in atmospheric science. When you do forecasting, you are learning a whole lot of things. And even if you don't know, I mean, there was a lot of material over some of your heads today, but you know what? You're going to learn it, and you're going to see it, and sometimes it takes experience and exposure to it before you finally start to catch on. Forecasting gives an incentive to continue going through the math, if it's a problem for you, and it's a problem for a lot of people. There are a lot of good thinkers in this country that don't follow math and don't understand math in the typical way that it's always taught. And this profession needs the people who think a little differently. Because somebody who's just mathematically adept at everything is going to be really good no matter how it's taught. But there are people who struggle with the math but have wonderful ideas. I think looking at some of the things that MIT was doing, well, somebody thought a good way to filter the radar display, and Greg, you were talking about that. That's a really great idea, and I don't think that's a mathematical, that's more of an artistic sense. That somebody says, we need to see it this way. We need to see it in 3 dimensions better. And so forecasting can be used as an incentive to help people pursue the stuff that is required, the calc and the physics that underlie what we're doing. Forecasting increases exposure to atmospheric workings. You ask any good forecaster and they'll tell you that it's part art. It's part experience, and there's an innate sense to forecasting. You can't always put it into words, but there is a feeling because your mind processes information differently than a computer. You have a lot of intuition and experience, and you don't necessarily have the ability to put it on paper, but you just know that something's not right. And forecasting gives you that. And I really believe that, and this is not against forecasting contests, but that's really no substitute for doing forecasting. Trying to figure out the temperatures and precipitation type at a station. And a lot of students will sit there and look at Moss and go, oh, that's my forecast, whatever, it's Friday afternoon, I'm going out. But spending 2 or 3 hours doing a forecast a couple of times a week, there's just no substitute for that. An experiment or a method that we're trying here. Which way? It's called Here's New York, no, California, which? An experiment that we're doing is something called a cognitive apprenticeship. And those of you who are forecasters, if you can be persuaded to come in and teach this, and this is kind of what we're doing here today, is we have a cognitive apprenticeship. The first thing is modeling. And that can happen in the classroom, that can happen in the lab room, where the expert, and we'll use the real definition of expert, gives some information out and says, okay, this is what it is, this is what I'm saying, maybe leads a map discussion, something along those lines. And then coaching, where you start to transfer that knowledge to the learner, where you start working with them. And this can happen only in the lab room. This isn't going to happen in the lecture hall. But you start coaching people, helping them understand it and grasp it for themselves. The next step is fading. And this is where the expert starts to withdraw and the student starts to pick things up and then only uses the expert on occasion to answer questions, to check the work to see if it's okay. And think about that in forecasting. Even with some of my students, I know from experience that they'll be doing analysis and they'll understand where the jets are, but they had a hard time picking up exactly, I don't understand where the shortwave trough is. And then you spend a little bit of time talking about PVA versus NVA, locating the trough axis, and they're like, oh, I get it, okay, I can do it. And then they start doing it on their own. And then the last thing is reflecting. Students now an expert and can work independently. And that's what forecasting allows. You can become experts at forecasting because you can work independently. You want to see how well you're doing? Just wait 24 hours and then go back and look at it. Forecasting offers a wonderful a category, something that you can do yourself and really motivate yourself. But it needs that initial kind of that push, that example to bring people into the weather lab, and it shouldn't be an intimidating place. We need to improve cognitive understanding. There is really no substitute for quality education, not just some lecture that's dry and boring and doesn't have much application, and the diagrams are still case studies from 1968. There's a lot of new stuff out there, and I think you saw it this weekend. People are talking about storms that happened last week, storms that you know about and you have something to reflect with. And it's not just dazzling with these wonderful displays. You get to the bare bones of it, and that's where the learning really happens. So just as a closing note, I would like to say if you've got ideas, I'd like to know your ideas about education. I'd like to know what things you need to see. I want to know if you're comfortable doing sounding analysis. I want, the things that we talked about in the conference this week. Did you understand it? Did you not understand it? What do you need in your educational systems to allow you to get to that point? What would you like to see? And then we as educators need to take that information and say, we need to think about our curriculum. These are the tools that people are using, and we need to be able to use the tools. And I think we'll be doing all of our students a great service if we start adapting to what's happening around here. So, does anybody else have any other comments that they maybe like to share? I'd like to just take a few minutes and maybe open it up to people. Roger.
I saw a geology homepage once that said that you cannot be a geologist unless you go out and see geology. I firmly believe that that's the case with meteorology too. You cannot understand convective storms unless you watch convective storms and observe them and try to relate the processes to what you've learned in the textbook and in these forecast labs. I don't think it's possible.
There's nothing worse than watching a model that you don't ever see happen. And you say, that doesn't work that way. That's not what goes on. And you got to know that. Eric?
I'd like to follow that comment up. Those of you who like to chase, might I suggest that you make a forecast in the morning and then go out and chase to where you forecasted and just see what happens. I don't think you're going to learn a whole lot about forecasting in the atmosphere if you're chasing with a television set and driving to the echoes you see.
I've always wanted to do a contest, forecasting. Everybody calls a point. You cannot drive 50 miles away from that point. That's it. No matter where, there's a supercell and there's a warning at County North. You can't leave your spot and see what happens. That would be, challenging. Chuck?
I've got to take issue with your comments about the expert, cognitive, whatever, about experts. I really believe that the model of an expert is wrong. Because that implies that there's some sort of level where all of a sudden you join the mystic fraternity, and now you become a dispenser of knowledge rather than a learner. And I would argue that virtually everyone in this profession still feels like a learner unless they're idiots, and then maybe some of them call themselves experts. But I think it's a bad model. I don't think it's a good model for students to look to someone as an expert. We are still trying to learn. The only difference between us and your students is that we've been wrong more often, we've said more stupid things, and we've failed more frequently.
Well,
I'll edit that out, Paul.
no, what Chuck is saying has merit in the fact of the way he defines the term expert. The model is excellent. In fact, it's that model that made me what I am when I started hanging around with people who were doing stuff. If it wasn't for Alan's passion about, oh, you gotta see this, and he started showing this analysis and the moisture conversions, blah, 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 I just went crazy. That was the expert coaching that I needed, because that rubbed off on me, and then I became good. And I would, say, what are you talking? I'd ask the questions. So whether Alan's an expert or Chuck's an expert, and I don't, that's not the point. The point is that's the way that you draw people in. And
yeah, but I think it's very intimidating for people to say, all right, well, I've got to achieve X level of something before I can consider myself an expert.
well, that's fine, but I'll never get an NSF grant if I just go nebulous words. I have to use something that they go, that sounds like
you say what you want to
pedagogy.
get funded, but I think you don't have to teach that way. And I don't like being taught that way, and I certainly don't like to teach that way myself. I think it's just wrong to carry the notion that at some point you join this mystic fraternity. That's just not the way it works. What happens is you learn and you have experiences. It's like I said today, some of us had to work very hard to find out how little we know, and we may resent people who come by their ignorance the easy way, but the fact is that we're still trying to learn. And that's really something that connects us to students, if that's the way you choose to look at it.
The students are going to pull you, they're going to be pulled in by what you do. You do not have to claim being an expert. And that's the real point. You don't have to say, oh, I know everything and you need to become like me. What you need to do is share that passion for what you're doing and say, this is cool. Look what you do when you do this, and see what this can be. And that's the educational process. Any other comments? Yeah.
I think that one thing that needs to be somewhat addressed in the future, probably starting now, is that humans are going to be here for a long time. How long we don't know, but I think it needs to spread also along the lines of going beyond the meteorological community. People who have a passion for it, whether you're a student, teacher, or enthusiast, I think that the public also needs to be educated on a certain level. It's going to come down to a point where you never know what the future is going to hold in weather. We have our patterns, we have our data, and so forth, but I think that people all over the world in general need some type of education early on, not just high school and college, but early. There has to be some type of education out there to lead people into this field, not necessarily for a job, but just to teach them in some way what's going on around them. Weather's going to be there every day. Regardless of what anybody thinks or says, it's there every day, and people have to live with it all over the world. Some way it needs to be expressed more that this is an important subject that needs to be appreciated and learned.
That's an excellent point, and you guys are the ones who can do something. There's not an elementary school teacher around that wouldn't want somebody who knows something about severe weather to come in and talk to their class and share that information with them. And, enough said there. Yeah.
Follow up really on this last comment and Chuck's. 6 of us piled into a van and drove here from Denver for one specific reason, and that was that you had undergraduate in the title of your conference. And because of the quality of the speakers that you brought to this conference, this is a very unique opportunity right here for us to talk openly about particular level of meteorology education. And for that, thank you. Appreciate this opportunity very much.
Well, good. With that, we'll end this part of it. We have just a couple of. I need an exit here. Okay. I just wanted to thank a couple of people. I wanted to thank Tom Mefford from the DuPage Office of Emergency Management and all of the volunteers. Great work. There's some special people I wanted to thank too. People who helped me put this conference together from the Weather Department, Dana Quinn, Matt Powers, and Jeff Milo. I want to thank my wife, Kathy, for taking the pictures and doing the web page and making it kind of fun and artsy. So, thank you.
Yes,
And all of the students, all of my students who have really been the reason that things like this are put on, because I want to make these opportunities for you, and thanks for the help that you've given, and so, yay. Thanks, guys. There's one other person I want to thank, but I'll take just I'll wait a minute. We do have a special award that we wanted to give, and actually Roger has it's an amazing award here, so please give Roger your full attention.
I decided to initiate a special award here in honor. It's a quasi-semi-super sub-annual award. In other words, I'm going to give it out as I feel necessary. But I decided that, as many people as are involved in storm chasing and storm observing, there's obviously the need for safety and education and spreading the word about safe storm chasing, storm observing practices. And so what I decided to do was give out an award on an irregular basis for devotion to and excellence in storm chasing, safety, and education. And I didn't know what to call it, so what I went ahead and did was named it the Meat Wagon Award. And this award is, like I said, for education, safety, and excellence in storm chasing. And I realized that the recipient of this award is going to be honored beyond belief. To have 7 photographs of the Meat Wagon hanging on his wall, and the award will also come with an authentic, honest-to-goodness piece of the Meat Wagon. And it could be something that fell off, or it could be something that I removed because it was about to come off. And in this particular case, it's several of them. This year, it's the authentic WSR 88D license plate from the state of Missouri. Off the Meat Wagon, as well as probably about a dozen flecks of the fake wood trim paint that keeps getting off. But without further ado, this year I would like to give the Meat Wagon Award, the inaugural Meat Wagon Award, to Gilbert Sabinski. Gilbert, as many of you know, has set up the Storm Chaser homepage, and he's done a tremendous amount in the last several years to get people to realize, with that big thing right at the front that says "New Storm Chasers Go Here," and to point people to essays like the one Al wrote, the one Chuck wrote, other essays on chasing and safety and ways to learn about meteorology before you get out and try it on your own. And I'd like to appreciate Gilbert's efforts for at least holding the Yahoo quotient down a little bit by getting people to really learn what they're doing, at least those that want to, before they go out and do it. And for that, I'm appreciative.
Roger, thank you very much.
times a week. I'm gonna have to live with this one.
It's more Gilbert Zone material.
More Gilbert Zone. I tell you what, before we introduce Eric, do you guys want to take like a real quick 5-minute bathroom break? Why don't we do that and then we'll get started. Just real quick 5.
They're rolling.
Okay, we'll get started here. We'll try not to make the mic too loud. It's not loud here. I have no monitors here. So. Okay, our featured speaker this evening is really, I'm just really excited about having him here. If the truth is known, Eric didn't remember me. I can't believe why.
Oh, I remember.
But back 18 years ago, Eric was the TA for my very first meteorology class that I took at the University of Illinois. And that was one of those times where I had no idea what was going on. But Eric, you had some video coming out of the back of a van, where you were storm chasing and running into the van and kept the camera going. And I thought, that is so cool. And that was like my first exposure to storm chasing. And it was kind of neat to see Eric, move through the ranks of being considered one of the nation's great storm chasers. And then he headed up Project Vortex. He was the field coordinator for Vortex. You've probably seen him on a lot of the TV shows, doing a great job defending meteorology and what it's really doing. And so it is my great privilege to introduce Eric Rasmussen.
I'm going to have my hands full, so I'm going to try to project and use the mic just like this. Thanks, Paul. It's really, this has really been an exciting conference. I'm really tickled to see the quality of the presentations you've had here, and I hope everybody's getting a lot out of it. And I hope I can follow on in that same tradition this evening. First I have to figure out how to turn on the overhead. I'm going to show some new findings from Vortex. Most of you know Vortex was a big field experiment in 1994 and 1995, where we went out with a whole fleet of geekmobiles, little sedans with weather instruments on top, and some mobile ballooning laboratories and mobile radars and a couple of aircraft. It was really a big experiment, a lot of fun to conduct. We've been working on the data, just trying to get the first tidbits of information out of it now for 2.5 years. And I feel like I've almost been possessed by this one storm. I just do nothing but analyze this storm. I'm starting to see some things, a lot of things I don't even understand, so it's going to be an interesting challenge this evening to try to help you understand. I'll do my best. The things I'm going to go over in this talk are, I'm going to talk about mesoscale inhomogeneities. Ooh, that just kind of rolls off the tongue, sounds so sophisticated. It just means that when you there's a lot of things going on that we can't even analyze on the weather map because they're so small in scale we don't have any data to even reveal that they're there. I'm going to talk about the role of boundaries in helping storms become tornadic. I'm going to go into detail, a case study of a tornadic supercell that we observed during Vortex. And then I'll talk a little bit about some new ideas about how tornadoes are forming. And I'm going to give the meteorologists in the audience some pointers on what they probably ought to be watching for on a day-to-day basis in supercell days. Oh, I'm Eric Rasmussen. I have a K in my first name and there's no S in my last name. And there's other mistakes, but I won't list them. Is that in focus? I guess it's good enough. My main co-conspirators are listed here at the bottom. Dr. David Blanchard from NSSL, and SIMS is a cooperative institute that sits between OU and NSSL. Paul Markowski is a graduate student at the University of Oklahoma, and he's the main reason I have some publications out there now. And Dr. Scott Richardson. Tom Shepard works at NSSL in Norman, and then Dr. Jerry Strzok at the University of Oklahoma is my primary co-conspirator. We have some sort of a deal where he inspires the ideas and I write them down and they get published, or it works something like that. But anyway, let's talk about those mesoscale inhomogeneities. It wasn't until about a year ago that I could even use words with that many syllables. This is a map showing what we call the storm relative helicity, and I'm going to talk in a few minutes about what that really is. But this is a parameter that forecasters use to give them an indication of whether an updraft in a thunderstorm is going to rotate, giving us a supercell. So that's all we're measuring with SRH. And I'll give a little more detailed definition in a minute. But let's look at this day, the 17th of May in 1995. Here's a map of the central U.S., and using these balloon soundings and the wind profilers and any tool we had available to measure the low-level winds, we estimated the storm relative helicity. And these are the numbers we came up with for that day. They vary from negative values at Midland and Topeka up to 400 and something over here at Granada, Colorado. And then in general, in the 100s, in the 200s, in the single digits, in the 10s, it just varies all over the place. That's the point I'm making here. And then if we go in this little box, we had a bunch of special measurements of the wind that we did with our own mobile ballooning laboratories and other sensors. And they're shown here in this box labeled B. The time you want to look for is about 0 Greenwich time, 0 universal time in parentheses. Look at those values, and you'll see that when you zoom in on a smaller area, the same sort of strange variation is going on. The values are all over the place. In fact, there was a tornadic supercell right up in here with a nearby value of helicity of 9, which most forecasters would tell you is something you shouldn't even pay any attention to. So the fact of the matter is that even with our denser network of observations, we can't tell at what scale those variations are going on, at what scale those variations are occurring. It could be that this thing we call SRH is varying this radically over, say, 5 to 10 kilometers, maybe even less than that. And so if we look at another number, though, this one's a whole lot simpler. This is just simply the change. This is the magnitude of the shear vector between the lowest 500 meters above the ground and 6 kilometers above the ground. So we just take the difference in wind and compute how long that vector is. And you can see on the larger scale in panel A that the variation, the numbers are all basically in the 20s. There's a whole lot less variation than we saw in SRH. And zooming in on the smaller region over here in panel B, the same holds true. The numbers are basically in the 20s at 0Z. So it turns out, for reasons we don't understand at all, that this larger, or this deeper measure of how the wind's changing the atmosphere doesn't vary near as much as this thing we call SRH. I want to tell you some of the implications of that. This is for the forecasters. Here's some of the implications of what we're finding. First, that if you send a balloon up and take a measurement and compute your SRH, your storm relative helicity, that number you come up with probably only applies to a very local area, especially when conditions are disturbed. Say there's thunderstorms around, or it's late in the day and you have all this normal variability in the boundary layer. So this calls into question a whole bunch of studies that have been done in the past where we say what we're doing is getting a proximity sounding. We send a balloon up near a storm with known severe weather, and we try to relate what's measured by that balloon to what this storm is doing. That may not be a valid approach, at least when we're looking at storm relative helicity. Number two, what I just showed you is the deeper shear vector, deeper shear measures like a 0 to 6 kilometer shear might be a better predictor of supercells because it's something that you can measure and you can have some confidence that what I'm measuring at this spot applies to that storm that's 50 miles away. This is a pure speculation in number three. It could be, and this is going to require a whole lot more research, that as a lot of you know, especially you chasers or spotters too, on a given day when there's several supercells in the area, a lot of times maybe only one of those will produce a tornado. And it's pretty mystifying what the reason is that one particular supercell gets chosen to be the blessed supercell and produce the tornado. It's possible. And like I said, this is just speculation, that these local variations in this supply of rotation, so to speak, these local variations are the thing that chooses this supercell. There's a whole lot more potential, there's a whole lot more rotation in the inflow of this supercell compared to those, and this is the one that's going to produce the tornado. Now, in another part of this talk coming up next, I'm going to show you one way that maybe we can infer that the storm relative helicity is much higher here compared to this county over here. And that has to do with the presence of a boundary, and I'll show you why that increases the SRH. But that may be our best hope. I can't foresee a time in the near future where we'll ever have dense enough observations that we can say, wow, the storm relative helicity is really high here, in this county over here it's not so high. I just don't think that we'll ever lubricant, that we'll ever have enough observations to say that, at least that I can foresee. The best we might be able to do is say, wow, it looks like there might be a boundary there, so we better be suspicious that the storm relative helicity is augmented in this spot. Oh, this last comment. Paul Markowski, after we got these manuscripts together on this topic, decided to look in detail at the photographs, those plots of how the wind varies with height. And he wanted to see, well, what's causing all this storm relative helicity variation? And what he noticed was that in one sounding, you might have this little loop somewhere in the photograph. The wind just changes a little, as you go up, it just changes a little bit, comes back a little bit, and then starts increasing again. On the photograph, that gives you a little loop. Maybe this thing's only a meter per second in magnitude, in its amplitude. That can cause a fairly major change in storm relative helicity, contrary to what we had thought for quite a few years. Or else this photograph is slightly concave, where the one next to it isn't quite so concave, and that led to a big difference in helicity. So the question is, okay, so that's what's causing the big changes in the numbers on the map. Does the atmosphere care? Just these last few weeks back at OU, Jerry Straka and Paul have been simulating supercells with the supercomputer. And they make these little changes in the wind profile that supercell is triggered in. I'm sorry, Chuck. Initiated in. And I've developed all these new sensitivities today.
In case of the model, it may be triggered.
Yeah. And it turned out that, in fact, if the model is really representing reality, and that's kind of a stretch, that in fact the model storms were quite sensitive to these little changes. The updraft speeds changed by 30% when you move this little 1 meter per second loop from 500 meters up to 1,000 meters above the ground. That's the only change you made in the whole photograph. And it changed the storm from looking like an HP supercell to a classic supercell. So we may be in really deep trouble here with some of this stuff, where we thought maybe 5 or 10 years ago that all we had to do was understand how much CAPE you had and how much helicity or bulk-Richardson number shear you had, and you could probably forecast the type of storm. Now it looks like there may be all sorts of sensitivities to all sorts of minor details that we hadn't anticipated before. That's the first piece of bad news for the night. I'll deliver a few more as I go on here. If you want to talk to me later about a climatology I've done that shows that helicity is still a good predictor of supercells, I'll get into that, but I think it's probably a little too much depth for tonight. In summary, a lot of the things we're seeing raise some interesting questions. For example, what's going on in a big outbreak day where almost every storm produces a tornado? Is there some real magic combination of helicity and CAPE that happens to be fairly uniform on a large scale, and so every storm produces a tornado? On other days, is that wonderful potential destroyed in a lot of spots, so only 1 or 2 storms produce tornadoes out of a bunch of them? And then on other days, maybe conditions are pretty crummy over a big region, but just here and there, they get enhanced, and you get tornadic supercells. There's all sorts of interesting questions like that we're starting to pose, and we frankly don't have a clue how to answer them at this point, but they're fun to ask. Boundaries. If you've been to the talks earlier today, you probably have heard a lot about boundaries. Boundaries are just, I'll show you some examples in a minute. This is just basically a small-scale frontal system, a mesoscale frontal system. I'll show you what we mean in more detail here in a second, but the types of boundaries I'll talk about will be boundaries that are independent of the supercell itself. In 1979, Chuck Doswell and Les Lemon put out what Al called, appropriately, a wonderful paper earlier today. And it has to do with supercell structure, and in that they showed a conceptual model of a supercell with a little storm scale frontal system coming out to the front of the supercell and another one trailing down to basically to the south and southwest. I'm not talking about those boundaries here. I'm talking about larger scale boundaries that happen completely independently of the storm itself. I'll talk about boundaries, this is a new kind that we've discovered just recently, that are generated by the shadow of the storm's anvil itself. And then boundaries that are generated by forward flank precipitation that's spread way out ahead of the storm. Get on to it. Here's some types of boundaries. This one we're calling independent of supercell. And I'm going to be able to see the picture this time. This is the situation on the 2nd of June in 1995, which is the day that has possessed my life lately. I wish I could rid myself of it, but it won't go away. This was a little cluster of marginally severe storms that formed in the middle of the day up here north of Amarillo and then moved to the east to the Texas Panhandle. It formed during part of the day where the shear wasn't very impressive and we would expect multi-cell type storms. In fact, that's what we got. And those storms produced a cold pool or cold outflow from the storm that spread southward and then westward to the Texas Panhandle as the day went on. I'll show you more about this boundary. I'm going to show you a case study of it in a minute. This is what we mean by boundaries independent of the supercell itself. This boundary was formed by earlier convection and then left behind as it spread here through the Panhandle. And here's another kind of boundary that wasn't recognized until some of the work we did here in the last couple of years. The boundary generated by the shadow of the anvil on convection. If you look closely in this image, there's big thunderstorm, cluster of intense storms here in the eastern Texas Panhandle, maybe some more up here in northern Oklahoma. They're generating a big anvil canopy, high cirrus clouds in the atmosphere. The sun is over. But it's casting its shadow right here along the southeast edge of the anvil. And if we look at we look at Oklahoma mesonet observations below that, we see that there's about a 3 degrees C temperature contrast right there at the shadow edge. And in some cases, we've seen these temperature contrasts up to 5 degrees C right at the anvil edge. Now, the only way this is going to work for you is if there's sunny skies. Otherwise, if this shadow is falling on some lower clouds like stratus or stratocumulus, that's not going to have any effect in the boundary layer in terms of generating a boundary. It has to be falling on in clear sky region, and it requires certain sun angles, obviously, to create the anvil shadow right there right there where you want it. Later in the day, it's not quite as effective, but this is an important. I think this is going to be an important feature to look for on days that are otherwise clear, except for an anvil, to watch observations below that shadow to see if there's cooling going on or a cessation in heating, if you want to look at it that way. I'll tell you in a minute why these temperature contrasts are important. I like to build up here things. And finally, in Chuck and Les Lemon's conceptual model, they had these little frontal systems associated with the storm itself. The precip is blown downwind here in the upper part of the atmosphere and then falls to the ground. If it falls through dry enough air, it will cause evaporation, and that will cool the air, leading to a temperature contrast right here near the edge of the rain. Warmer air in the inflow here and cooler air because of the rain here. And we believe that we have observations to show that happens sometimes, but in a lot of cases you don't get that. And the reason you wouldn't get this temperature contrast is if the air below the anvil there is already very cool and humid. If you rain into it, there won't be enough evaporation to make a difference. It's got to be relatively drier and warmer, and then when you rain into it, it'll cool it off and give you a temperature contrast. So you may think that's a trivial point, but it's not, because what I'm going to show you coming up is that a whole lot of these tornadic supercells occur on the cool side of boundaries where it's cool and humid. So in those cases, you really wouldn't expect much of a boundary or a little frontal system there on the front side of the storm. How important are boundaries? I can answer that, at least from a small sample. In Vortex 95, we counted all the tornadoes that occurred in the vortex region, which was the Central Plains essentially. And the tornadoes we counted included those that we saw in vortex, plus anything else that made it into storm data that was F2 or greater. Now, when I do studies like this, climatological type studies, I will not count F0 and F1 tornadoes from storm data because by and large I don't trust them. I think they're misreported way too often, and they have a tendency to really mess up a statistical study. So we chose F2 or greater, or tornadoes that we witnessed of any strength. And this is how the counts came out. We had 44 tornadoes. 28 of them occurred very close, within 20 kilometers, of boundaries that were either completely independent of the storm that produced a tornado, or the boundary was associated with a cirrus amble canopy. 10 of the tornadoes out of 44, we had enough data to say whether or not there was a boundary, and we could clearly say no, there was not. And in 6 cases, our data wasn't sufficient. But the big point here is that in the majority of cases, during 1995 in the Central Plains, tornadoes occurred in close proximity to boundaries. I would really like to turn this into a nationwide study, a multi-year study, and I think we're taking some steps at NSSL to move that direction to determine if this is true nationally. I believe it probably is, and to me it says a lot about this quote-unquote tornado problem in various other parts of the country where their storms just aren't like those Great Plains supercells. I think probably in other parts of the country there's a lot of tornadoes because of storm interactions with boundaries. I think it's also true in the plains, but we just weren't sharp enough to realize it in the past. We were wrong about our Great Plains tornadoes, not about those in other parts of the country. What might a boundary do in terms of promoting tornado formation, or at least intensifying a supercell? Ooh, math. Right. This is where you boo, right? Let me tell you something about math. When I was an undergrad, I hated math too, and I probably would have been one of those cheering in the audience just a minute ago. But we can't do this science without the math. It's great to know, it's great to understand the physical model and have pictures in your head, and that's how I think. I think in terms of pictures. But we can't prove or disprove any of this stuff without the math. Sorry, that's the price you pay, I guess. A boundary, in simple terms, if we have a boundary, that by definition means that on one side the air is cooler and on the other side the air is warm. This boundary is the place where the cooling begins. That's the edge of the cooler air. So between this air and this air up here, we have a temperature contrast. And in the simplest terms, just like Al showed this morning, if you want to visualize it this way, the air tends to cool and sink and spread where it's cool, and rise and go the other direction where it's warm. So if you have a temperature contrast, and this is now a small scale thing, say a lot of this temperature contrast will occur in 5 to 10 kilometers, but if that's there, you tend to set up, you generate horizontal vorticity, which is rolling motion of this sense in the atmosphere. Now, why should that be important? Well, it's really quite simple. If I have a thunderstorm updraft moving along here, drawing air up out of the lowest levels, and it comes across the boundary, all of a sudden it sees this air that has a whole lot more horizontal vorticity. It can tilt that into the updraft and then stretch it and produce much more intense rotation than if that weren't there at all. So that's the simple effect. It's especially helpful to the storm if it can move along this, because then it can just keep seeing this vorticity-rich air as it moves along. This is where storm relative helicity comes in. If we take that part of now obviously the horizontal rolling motion, if you want to look at it mathematically, you can have 2 components. One is this way, the other is this way. They're both horizontal. To the degree that the horizontal vorticity is oriented parallel to the wind, we call that streamwise vorticity. It's vorticity that's along the stream. And that is the stuff that gives us storm relative helicity that can be taken and turned into updraft net rotation. There's a lot of places you can get the details on that if you want to know, and just ask me. But that's, I think, what the boundaries are doing to the supercells. The supercells are, I don't know who's doing what to whom here, but when the supercell arrives into that vorticity-rich air, then it can rotate much more strongly in low levels. Another possible role, which has been proposed by Wakamoto and others, is, and it really can't be refuted right now from the data we have, is that that there's these things, these mesocyclones along a boundary, which is just a little wave here, or a little vortex embedded in the boundary. And now this has vorticity of a vertical sense, as you can tell just from the plot there. We're looking down on the weather map. And if a storm moves over that, obviously it can it can converge and stretch it in the low levels and also develop a vortex that way. That has been suggested as the cause of a couple of tornadoes in vortex, I believe, and in those cases, I believe I can refute that claim, and we're in the process of doing that. I'm not sure how often this really is important in supercells. I'm not saying it's not important, I just don't know. A case study to illustrate these ideas is the 2nd of June, 1995. Memorize that date. You're gonna, well, you'll know it by heart by the time this talk's over if you try to memorize it or not. These are the things I'm going to show you. The origin and the structure, or the origin and the behavior of the boundary that day, what its structure was in terms of what it did to the winds, what it did to the behavior of all the storms. This was a great laboratory this day because we had at least a dozen supercells. I don't know if I've counted them. It was at least that many in West Texas. And it turns out that the supercells that crossed the boundary or interacted with the boundary were quite different from the others. I'll show you that in a minute. It was nice to have so many storms, some on one side and some on the other side, so we could look at the differences. And then I'll show you an example of what happened to two particular storms as they crossed the boundary. And here it is again. I showed it to you a minute ago. This is a little bit earlier in the day. I need some clean freeze sheets up here. This is closer to the time that the boundary first formed. There's that convection north of Amarillo, and the boundary is coming out to the west and south. And then as time goes on, here's the isochrone analysis. 19Z, which is early afternoon, and then every 1 hour there's a new line showing the position of the boundary here as it marched on all the way out into New Mexico. And actually marched up the terrain. At about early afternoon, 1949 UTC, the Peakmobile Armada passed through the boundary to the southwest of Amarillo. Now these cars were able to measure temperature, pressure, humidity, position, and wind all day long. They made a measurement every 2 seconds. Those were average, and we saved them every 6 seconds all day long. So it's tens of thousands of observations from these cars. And it's about 3 meters above the ground. It's a wonderful data set and all sorts of nice things you can do with it. But as the car approached the boundary from the northeast, its temperature was about 21 to 22 degrees C, northeast winds. And then right at the boundary, at a distance of about 500 meters, the winds shift from northeast to east-southeast. And the temperatures went 23, 24, 25, 26 C. So there's about a 5 degree C temperature contrast. Begins right at the boundary and extends back into the cool air. All of that temperature change occurs in 5 kilometers, about 3 miles or so. And then later in the day, the Armada turned around and headed back the other way. That's the way it usually went. We were kind of just chasing all over the place, having the storms chase us half the time. And the boundary still looks the same. This is out near Bovina, Texas, where Howard Bluestein once grazed on the clover. That's a true story. I have a photo of this. The temperature is 22 degrees C, like it was earlier, on the cool side. Winds have gotten a lot stronger out of the east-southeast, 30 to 35 knots back here in the cool air. South side of the boundary, the temperature is back up to 25 to 27 C, with basically south to south-southeast winds at 20 to 25 knots. So the boundary looks quite a bit like it did earlier, at least in terms of temperature contrast. As it approached Lubbock, which is in the south of the Texas Panhandle, about 40 miles, but right in the middle of that part of West Texas. This is the reflectivity on the 88D radar, which is color-coded to bring out, I think 15 dBz is the red. So this is the low reflectivity stuff. Fine line along the boundary is probably bugs, where the air is converging and bugs get carried up. They really don't have the strength to fight that, and it shows up on radar. But I'm going to show you what I've done is, I got to get physical here. Well, I took a line that cuts right through the boundary, perpendicular to it, and I looked at the lowest 4 scans, so that gave me a cross-section of the winds through this thing. I want to show you what the boundary did to the winds. And this is that. Let's see, what's most useful? Here's the height in kilometers above the ground, or some of you might want to say kilometers incorrectly. This is the distance from Lubbock at 45 kilometers, and then here is this black bar represents that thin little colorful line, that fine line along the boundary. It's right here, and then you go further into the cool air as you go off to this side.
right at the boundary, the winds were coming toward the radar at a little more than 3 meters per second. And as you go up in the atmosphere to about 2,000 meters above the ground, the winds are blowing away from the radar at about 13 meters per second. And if you compute the difference between these winds down near the ground and the winds at 2,000 meters, that gives us an estimate of the part of the horizontal vorticity that is parallel to the boundary. Okay, there's two parts. One is perpendicular to the boundary, the other one's parallel. So the parallel part on the warm side of the boundary is about 5 times 10 to the minus 3 per second. Right at the boundary, it jumps up to 10, and it stays up in the 8 to 9 to 10 range as you get off into the cool air. So this is exactly what I was showing you in that conceptual model a minute ago, that just because of this, the 5 degrees C temperature contrast across here, we've generated a whole lot of this stuff. In fact, we've doubled what was there already. And what is this 10 times 10 to the minus 3 per second? Is that big or little? I keep hearing these questions thrown out today. A mesocyclone, I believe, if I remember hearing right, starts at about 1 times 10 to the minus 2 per second. That's how fast the spin is in a supercell updraft. That's exactly what this number is. What that means is all we have to do is take it and tilt it. We don't even have to stretch it, and we've got a supercell strength rotation in the updraft. Don't ignore these boundaries. It's amazing how strong the vorticity is along them. Just on the back of an envelope, and this is proof, I went through the exercise of computing how much vorticity you can generate. And in fact, if you have a region 5 kilometers across which the temperature changes 5 degrees C, that's not a big thing, not a big deal. And a parcel of air sits in that for 10 minutes. It'll have 1 times 10 to the minus 2 per second spin, mesocyclone strength spin, but in the horizontal. So air just has to be in that region for 10 minutes, and it's already got that much. Now, of course, friction's acting against that, and there's all sorts of complications. But the point is, no matter how you want to reduce it or enhance it mathematically, it's going to come out to be a number that you have to pay attention to. What did the boundary do to the storms? Well, I've heard some pretty crude names for this picture, but I won't repeat them. This is I can't help it. Mother Nature does things like this. What I've done here is I'm showing you the tracks of the highest reflectivity in all the storms that day. Now recall I told you a minute ago that these were all supercells. That is true, at least in the sense that they all had pretty decent mid-level rotation. The first hour's action is the black squigglies here, and they're in eastern New Mexico. Next hour is the blue ones, and you can see that they're getting closer to Texas, and there's more of them forming further south. Then we go to red, same trend. They're getting into Texas, and they're still forming further south. Green is the next hour, 0 to 01 UTC, are the green arrows, and then purple. Now, look a couple of things. These are the boundary positions with the same color coding. The red circles are the tornadoes that occurred this day. There are two or three more up here in eastern New Mexico. I can't remember the count. Those were just on the cool side of the boundary, within about 20 kilometers. And you can see that all of these tornadoes in the circles were also just on the cool side of the boundary, and most of them within about 20 kilometers, although a couple of them were a little further out. These were all significant tornadoes, and the point here is that these storms were supercells and cause for concern, that the tornadoes were all clustered in this little tiny narrow region. If you wanted to put out the perfect tornado watch, it would have been about a 40 kilometer wide strip on the cool side of this boundary. But also notice what happened to the storm motions. They were all kind of just trucking along to the northeast. When they interacted with the boundary, they turned off to the east and started meandering. Some of the storm formed right on the boundary also just kind of meandered off to the northeast. That's what the boundary did to the storms. I think it's a pretty significant finding, and one that bears watching and is worthy of some much larger studies. Now, just briefly, because I want to get into this case study, two storms in particular. There was a supercell that happened near Friona, Texas, produced an F3, I believe, although some of the damage I saw looked more F4-ish, but I don't make the ratings. Chasers always tend to overrate tornadoes anyway, but in this diagram, this is time goes this way. Don't worry about the time scale. I chose a really crummy one here, and I apologize. It's it's seconds from after 2300 UTC, but I'll translate this into something more useful here in a second. This is the elevation angle of the radar, and over here is the height of the radar beam. So, and the heavy contours represent a measure of the strength of the rotation in the storm. It's the differential velocity from the strongest outbounds to the strongest inbounds on the Doppler. This area, between these two black lines is a height containing some pretty decent rotation, enough to perhaps even issue a warning. The storm comes along and crosses the boundary at this time, where I have the heavy black bar. Immediately we see much stronger rotation, a quadrupling of the differential velocity here at about 3 to 4 kilometers above the ground. And that built upward and downward with time through the storm, and then a very significant Fiona tornado was produced at this time. This is a fast process. The boundary was crossed, immediately rotation ensued, and then about 1,000 seconds later, which is less than 20 minutes, 17 or 18 minutes, we have a major tornado on the ground. I'll show this over and over in this talk, that the evolution in these supercells is remarkable, and I don't think these are exceptions. I think perhaps we just misunderstood a lot of the supercells in the past. We saw a mid-level meso for a couple hours, and we thought, well, this is all going on gradually, and then a tornado forms. Well, I don't think that's the case. I'm not sure, I'm not convinced just how related that tornado is how related it is to the mesocyclone, but at any rate, the process of tornado formation and the process of the big spin up in the low levels of the storm is a very rapid process. And then at Dimmitt, and this one makes a nice transition to the next part of the talk, because this is going to be the storm I'm going to show you in detail. Again, the boundary was crossed here. Immediately at this height, we have a quadrupling to a quintupling in the differential velocity. That strengthening spreads downward and upward with time. There's a cessation in spin here, which I can't explain. I finally figured out what's going on. I'll show you that in a minute. Then immediately it picks back up again to the whole depth of the storm, and the tornado is produced at this time. So again, about, well, this one takes a little bit longer, more like 1,500, 1,800 seconds, which is about a half hour. All right, let's go into a discussion of the Dimmitt. Is it a discussion? Are we discussing? No. Let's don't discuss the Dimmitt supercell. I talk, you listen. Oh yeah, I'm an expert. Thanks a lot. That really hacks me up. I'll show you everything I don't know about this one. This is going to be chronological. This part of the talk will be in chronological order. 0057 UTC is when I would say the tornado formed, but that's kind of a silly, I've decided it's a pretty silly statement to say the tornado formed at this time, because what's going on is a process of intensification. It finally gets strong enough for a little dust to start whirling, and then it gets a little stronger and the funnel starts to descend. There's no real time when you've got a tornado there, unless you're going to define a tornado very specifically as a certain wind speed. But at 0057, we really started picking up a lot of dust, and then a minute later the funnel was to the ground. So that's kind of the picture to have in your head. Now, this slide, in one snazzy slide, summarizes the evolution up to the time of tornado formation. These little clocks tell you what minute we're at. The faint minute hand is the time the tornado formed. So, and it reads from top to bottom down each column. So you see here we're about 20 minutes away from tornado, and then about 10 minutes away, and then get closer and closer, and finally we get to tornado time. The shaded region with the contour is about 30 dBz, and a whole lot of the storm is off here. This is just the appendage, the southwest part of the storm. Geographically, Dimmitt is where the roads come together, and you can't really see the faint section line roads unless you have really good eyes, but basically between this heavier road here and US 385, that's 6 miles. I'll try to hold this steadier. I don't know if I can do it. 6 miles from, the more I try to shake her, it hits. Finger widths, there you go, 6 miles. No one else in this room could do that, I don't think, at least not you guys. All right, the heavy little line that runs down through the hook is the low, where the reflectivity is the highest. So if you look at the picture, you'll see this little band of higher reflectivity snaking down through there. At 0038, we have a mesocyclone near the edge of the range, above the edge of the range here, the low-level range, near the edge of the weak echo region, which is where you don't see precipitation. There's an anticyclonic vortex that we detected using Dow radar right down here in the appendage itself. Go 2 minutes later, and Dow radar is now showing a couplet of vorticity there. What that means is there's a place with cyclonic or counterclockwise rotation right adjacent to one rotating the other direction. By adjacent, I mean within a couple miles of each other. I'll show you more detail on that in a minute. 0041, now we're 16 minutes before the tornado. The appendage is starting to shrink and weaken. Mesocyclone's right here at the edge of the brain. 0045, now we're only 12 minutes from the tornado, and the appendage is almost gone. And this is that period of cessation in the rotation I told you about. The whole storm is really crapping out. For reasons, it's not clear. It may have been a kind of a cyclic storm that tried to spin up, put out a gust front, and then went through the whole process again and finally made it to tornado. But at any rate, we're only 12 minutes from tornado time. This storm is not impressive, believe me, on 88D or any of our sensor systems. At 0047, 10 minutes from tornado time, now we've got a mesocyclone out here in the weak echo region. And all of a sudden a blob shows up. I don't have a better name for it. I'm going to call it the blob. We have an appendage, and then a few miles south of that, a little blob of precipitation. And Dow radar, which is a Doppler on wheels, our mobile radar, which was parked right up here, was seeing a vorticity couplet, a counter-rotating pair of vortices right there at the edge of that blob. 6 minutes before the tornado, the blob is continuing, and we're starting to get a little tiny thin curtain of rain between the main appendage and the blob. And 5 minutes before the tornado, the mesocyclone now appears to have a split structure with a strong vortex here, 2 miles east, right over the highway, another strong vortex, and an anticyclonic vortex here at the south side of the blob. And we continue on. Nothing really remarkable to show until about 2 minutes before tornado time. Here we have a slot, an actual radar reflectivity void. This is similar to the things Ron Presbolinski was showing. What was he calling those things at the back of the channels, the low reflectivity channels. One of those is cutting into the appendage right here, giving the idea of strong cyclonic rotation and dry air intruding there and evaporating the rain. And then right at tornado formation time, this part of the mesocyclone is not so apparent. What completely dominates the WSR-88D field is the tornado itself approaching the highway here south of Dimmitt. And just looking at the tracks, you're able to track certain features in this. For example, the blob itself, this channel cutting in, this little tiny shower down here to the south of the main appendage, there, and there. If you track those in time, you can get their speeds. This part, the mesocyclone part of the appendage, is moving north at 12 meters per second. The channel is cutting in at 46 meters per second, 90 knots is how fast that echo is moving. And then you go further south, the blob here is moving at 18 meters per second, and this little tiny thing is almost sitting still down here. What does that tell us just about the large-scale flow in the backside of the storm here? Well, it tells us there's a lot of cyclonic vorticity here, because look at the difference in velocities over about a mile, 12 meters per second to 46. That's right where the tornado is forming. And then rotation of the other sign, perhaps on a larger scale, just to the south of that.
Is that the clear slot?
Say again?
Visually, is that the clear slot?
That is a clear slot. I'll show you that in a second. Now, in detail, let me know when I have about a half hour left, okay, Paul? My voice isn't going to last that long. Let's look at some of the details. Now I'm going to back up. No, excuse me. This is where it comes in handy to have two projectors, but I think I can pull this off. We're going to go back to 0048, which is roughly this panel up here, as Chris would rather say, up here. I'm going to show you details at 0048, 1 minute after this, which is right after the formation of the blob. I knew I should have had a couple beers before I started this. Here's the world's crappiest depiction of reflectivity. It looks really nice on my workstation, but it just did not make it to the transparency. What I've done here is all of this this grayishness up here is reflectivity from the belly radar of our aircraft. It was just a red conventional X-band radar. The darkest gray is the heaviest rain from Dimmitt west and southward. There's a couple of hail reports at the ends of these arrows, ranging from 1 centimeter up to 2.5 centimeters, right down in this part of the storm. Now you can see kind of a break in the grays here. This is because the Dow radar was parked right here, scanning the very lowest parts of the storm, right below the cloud. and I've put their reflectivity in this section here. And I'm going to have to trace this with a marker to really make it clear, if I can even see it myself. It's really tough. Here's the center of the appendage they see. Oops. Oh, this is tough. And then it turns and goes this way, and then there's a blob right in here. And it even actually trails on down in here somewhere. But that's roughly it. Just a very thin little veil of rain, about not even a quarter mile across is what the appendage looks like on the Dow radar. Other things you see in this picture, these are mobile mesonet observations. Again, strong inflow into the storm, 25 to 30 knots. Some places even stronger. These are the temperatures analyzed, 21 degrees C and warmer, and 20 degrees C and cooler, but that's not a heck of a lot of temperature contrast near a big old supercell. You'll see a lot more than this in a few minutes. There were some ideas that it was a low-level temperature contrast right at the storm that was giving rise to a lot of rotation in the air, horizontal rotation that was then drawn into the updraft. But in this case, that certainly wasn't true. Now, something to keep in mind, we've got a boundary down here, the one I showed you in the case study. On the south side of it, it's close to 30 degrees C. So we've got a tremendous temperature contrast down here to the south of the storm. And that gives rise to a whole lot of horizontal vorticity right in the inflow of the storm. In fact, for you storm relativity fans, we've estimated it at around 1,100 meters squared per second squared in the inflow of this storm. What else is in this picture? T is where the tornado will come down in 9 minutes, right there. This gray outline with the red stippling is what I'll use to denote the base of the thunderstorm. That nice flat cumulonimbus cloud base, the lowest part of the cloud base. It's not a wall cloud in this case. The whole supercell has this uniformly low base, and we never see the lowering like what we usually call a wall cloud. But this is the northern part of the base. My photographs ended here as Bobby Edens looked off to the west. So I can't tell you at this point how far south that storm base goes. Finally, this black line represents the storm's gust front on the edge of the rear flank of the storm. Here's some more detail from the Dow radar, the Doppler on wheels, looking up above the ground. At this range, he's looking at 1,500 meters above the ground. At this range, it's up to 3,000. So this is just a scan that tilts upward with height. And the grays, again, or the reflectivity, are how much power is coming back from the precipitation. At this time I've outlined it for you. We have kind of a cyclonic-shaped hook here, turning into kind of an anticyclonic-shaped hook on this end. These are the radial velocities we're seeing. So these are going toward the radar. Right in here, they're going away, and then they return to toward again. And what this gives us is an anticyclonic vortex right here, and a strong cyclonic vortex right here. Excuse me. Some of that Italian sausage. No, that was crude, I'm sorry. How strong were those vortices? Would you believe TVS strength? Both of them. The anticyclonic vortex was the strongest by just a few percent. I believe we were looking at 38 meters per second shear on those two vortices. Here we are closer to the ground, and there again is that funny shaped hook cyclonic, then coming around kind of an S shape to anticyclonic further south. Here's the storm's gust front. How do you know it's there? Well, these are the Doppler radial velocities right at the ground, 0 degrees elevation, so at least within 100 meters of the ground. See this big change in the wind, the radial velocity right along this line, from strong inbound to a little bit of nothing. That's the storm's gust front. So what does all this tell us? Well, if we combine what we're seeing here, we would assume that there's a downdraft back in here somewhere that's giving rise to this gust front, this storm gust front. We look at the reflectivities here, and we see there's nothing in the Dow data. This is a very sensitive radar. I can see down to minus 15 dBz at this range. If there were any bugs or raindrops out there, we would have seen echo, but there was nothing. What does that tell us? It tells us that pristine air, clean air from aloft was sinking down into that region. That's about the only good assumption you can make, I think, when you see the reflectivities go to undetectable on this radar. So, and remember, we have a cyclonic vortex here aloft and an anticyclonic vortex here aloft. The big picture is almost irrefutable, I believe, is a downdraft here straddling, with a pair of vortices straddling the downdraft. Air sinking, and on one side of the sinking you've got cyclonic rotation, on the other side of the sinking anticyclonic. So a lot of other evidence for that in the storm, but I don't want to get into dwell on it too much. 2 minutes later, the big picture, the temperature contrast has not improved and has not increased. Now we have a better map of the storm updraft because I've got two photographers looking at it here. From down here, Matt Crowther of the Weather Channel and Bobby Edens, a chaser from Midland, I believe. Fort Worth. Now in Fort Worth? Or always Fort Worth? Okay. The supercell updraft base with its red stippling and the storm's gust front. And I'm going to show you airborne radar data from this red box and also from two slices through the storm, at A and at B. And there's the blob, by the way, right there. Oh, one thing I wanted to comment on here. Supercell updraft, I don't know, maybe just as a naive storm chaser, when I was out looking at supercells and photographing them over all these years, I thought I was looking at a big storm, a big updraft. And now we measure the cloud base and map it out on a map like this for the dimmest storm, and I'm looking at an updraft that's 1.5 miles across east-west and maybe 4 miles long north-south, which is much smaller than I ever pictured a supercell updraft being, especially considering that this little center of rising air, where most of the rising motion of the storm, the air goes right through this region, is capable of spewing out this huge region of precipitation as the air diverges aloft. So that was kind of a revelation to me as I looked at all of this stuff. Now let's look at this red. Remember where the red box is? It's basically contains the blob right in the west middle part of the box, and the storm's weak echo region here in the middle. The center of the box, and then the edge of the precip core in the northeast part of the box. I'll put that up again in second for your reference. Let's see, I want to show that one yet. Zoom will be fine. Okay, 3 different heights, airborne radar data. On these research aircraft, they have a radar in the tail that scans like this, kind of a helical scan, up and down, sort of like an RHI scan. And then I take those and assemble them into a horizontal map in that red box I showed you. At 1,300 meters above the ground, here's the blob. Here's a little bit more of the hook extending on beyond the blob, and there's the edge of the main rain core. We can see very strong velocities down here in the velocity panel toward the aircraft. Dark blues here are about 15 meters per second. Bright reds, and that'd be toward the radar, or toward the west. Bright reds are represent velocities of about 45 meters per second away from the aircraft. So what we've got at the low levels, 1,300 meters, even the aircraft that is now coming on site sees cyclonic rotation right here between the blues and the reds, and anticyclonic rotation not more than 2,000 meters away between the reds and the blues. And then you go to 2,800 meters above the ground, and we start to see a mesocyclone. And it's got, of course, the velocity toward here and away here, and the meso centered right in the middle. And then you go above that, and the meso is tilted off to the northeast. We see very strong flow away from the aircraft. What else does this show us? As you go higher and higher in the storm, looking at the reflectivity, we see that what is just a blob at the ground is a more solid-looking appendage of precipitation here. You get up to 5,800 meters above the ground, and you have a solid curtain of precip all the way around the south side of the storm with a bounded weak echo region, or beware, up here. So what does it tell us about the hook echo, at least in this storm? If you picture in your mind this thing we're calling the bounded weak echo region at B, it's a cap of precipitation over the updraft, surrounding it on all sides and on the top. The hook is where that precipitation has come cascading down the rear side of the B rear, down the west side, until it reaches the ground. And then a bit further south, it hasn't made it yet. And so you don't have a complete circle of precip in the lowest level. So what this is just a downward extension. I'll show you this in better detail in just a second. That's just a downward extension of this big echo here. Something else to note, my little pair of vortices is not hooked onto the meso. The meso is higher in the storm, and it is good 6 to 7 kilometers east of that vortex pair, which is right there on that downrift of the very back side of the updraft. Now, going back to reorient you, I'll show you cuts, vertical cuts, cross sections through the north side of the updraft, north of the blob, and right through the blob itself. So here comes those two pictures. Confusing myself here. These are vertical cross sections, again, reflectivity and velocity. So here's north of the blob. We're cutting through the storm's updraft here, where there's very weak reflectivity. This is what you've seen in a number of talks today called the bounded weak echo region. In this storm, it extends up to 10 kilometers. In some of our vortex storms, it extends all the way to the summit of the storm with this tiniest little cap right on the top. In fact, when you look at all of the supercells in vortex have bounded weak echo regions extending to very deep levels. It's just, we have high resolution radar, so it's very easy to detect them. And this is, again, north of the blob, north part of the updraft. There's that curtain of precip coming all the way down the back, reaching the ground as a skinny little hook on the west side of the updraft. Something I want you to notice that you'll see in several panels. This is the air flowing westward. This is the inflow of the storm. It starts rising up and welling up in the updraft. You'll see this a lot more vividly later. And there it encounters ambient winds from the west at about an equal speed, giving rise to a whole lot of strong convergence, at least in this component of the velocity, right at the hook echo. And then if you go further south, well, one other thing to notice here, the difference in velocity between the surface and, yikes, and 3,800 meters above the, sheesh. Let me make sure I'm right. Let me throw this back up just a second. I don't want to bore you with too many facts, but this really impressed me a bunch. If you go right here on the north edge of the meso, in the north part of the updraft, at the ground 15 meters per second to the west, and aloft at 5,800 meters, you're out of the west at 45 meters per second. So there's 60 meters per second, or about 120 knots wind speed change from the ground up to 5,800 meters, right there at the edge of the updraft. Back to the cross sections. If we go through the blob, there's the blob. There's a shallower weak echo region there on the middle part of that area, the middle part of the weak echo region, and very strong velocities aloft, which is basically just the south edge of the mesocyclone aloft up here. You know, you're probably sitting out there thinking, why is he showing us all this stuff? And it just occurred to me that I did not tell you why I wanted to show you all this stuff. Oh, fine. Now he tells me I have a half hour as I fumble around for... Oh, here it is. A few things to notice as I go through this. The speed at which things happen. Mother Nature's doing all of this in about 10 minutes. It's taking me 40 minutes to go over it. This is very fast stuff. That's a cause of concern, I think, to anybody who does warnings and spotting. Once things start to happen, you have to be on top of it because Mother Nature's not going to cut you any slack. It's a fast process. The importance of the downdraft and how it's associated with that pair of vortices, one rotating one way and one rotating the other, is something I want you to pick up on. Also, you'll notice here just in a second how very occluded this system is before a tornado ever forms. By occluded, you'll see in a second that the gust front goes surging out and wrapping up well before the tornado forms. So here we go, 5 minutes away from tornado time, 30 minutes away from the end of the talk. Here's my cloud base again. Now look how it's changed shape. It's getting this indentation in the back, which is what storm spotters and chasers call the clear slot, which is one of the most key cloud features, I believe, in terms of predicting tornado formation. The blob is right here in the back side of the clear slot. The updraft itself has got this horseshoe shape, or kind of an inverted, backward C shape. And the gust front, still and always, as you will see, is right underneath this CV, this cumulonimbus cloud base, and is starting to take on a very distorted shape here as it surges out to the east, right ahead of the blob itself. Tornado's going to form right up here. How the heck do I come up with that cloud-based map? This is one of the things that I think is teaching me more about the Dimmitt storm than practically any other tool I have, are these cloud mappings. It's really a straightforward process. There's that same cloud-based shape I showed you. I had a photographer, Bobby Edens, I didn't have him. He was very gracious to let me have his video. But he was parked right here, just east of the updraft, almost in harm's way, but not quite. This is a panorama of images from his video, looking basically north at the edge of the CV base, kind of arcing up here over the highway, through northwest. You can see the tail end of this part of the head, basically I don't know, I've got to be careful what I call this thing. But this cyclonic part of the CV base, its tip right out here is this thing. And then right through here, it's hard to discern in this photograph, but it's quite obvious in the video, is a region where the clouds are being evaporated. We call that the clear slot. and it's surging very quickly eastward through this entire CV base. CV means cumulonimbus, and it's a type of cloud that a supercell is. And then Matt Crowther was just a little bit further south, and so using triangulation between his images and Eden's images, we just come up with this map of the cloud base itself. Further south, there's the tail end, the south end of the bell-shaped cumulonimbus base, the clear slot cutting in here, and then further back, this more cyclonic part of the base, which will eventually form the tornado. Okay, right at the tornado time now, actually a minute passed, and look at the change. This is the same scale map. Am I lying? Oh, rats, I think I doubled the scale. Oh, shoot. Take it from me. Trust me on this one. This cumulonimbus base has grown enormously over just the few minutes that took that slot to cut in there. But we now have a very spiral-shaped CV base. There's the tornado right there in the gray dot. That's how big it is. It spirals outward to the north, east, and then back to the south. And associated with this surging gust front and the fact that the air is converging or flowing together along it, initiating more updraft, the storm's updraft has now grown and elongated a whole lot just over the last few minutes of this analysis. Now we start to bring in mobile mesonet data. I'll show you where these streamlines come from in a minute, but I believe I have a lot of confidence that that's where they are. First, here's the hook. You see this little skinny band of gray coming in to the tornado right there. So the tornado is right at the tip of the hook. And this is where the surface gust fronts are located. One comes spiraling out of the tornado to the north, right under the CV base, and then ascends southward. Now there's another front extending north. Why is that there? Air is sinking all through this region on the backside of the storm and along the hook and spreading at the ground. And that diverging flow is giving rise to the presence of this front and a beaver's tail cloud extending northward from the cumulonimbus. So notice how how wrapped up and spiral this is at the time of tornado formation. Bob Davies Jones from NSSL likes to have tornadoes right on his bumper, so he did it in this case. And by doing that, he managed to sample 3 air masses: the air coming around and including, quote unquote, the tornado, or wrapping around in the downdraft, the inflow to the thunderstorm itself right here, and then more spreading downdraft air up here to the north of the tornado. Kind of a neat data set. Keep in mind, an important point here is that this downdraft air, including a clear slot, the evaporation of cloud, which you see here, has wrapped all the way around the system except for one little piece here by the time the tornado forms. That would make us believe that what we call the rear flank downdraft, that wrapping downdraft, must have some key physical importance to the formation of the tornado itself. At let's see, this is the same time, 0058, the radar, airborne radar is showing a hook. It's blurry because these radars, even though they're high resolution, they're not quite high enough for what we'd like to see. But here's the hook, comes southeast, wraps up into a tight little spiral, and then comes back out again, and wraps back down, and here's our blob marching right along. Associated with this system is a void in the reflectivity, a minimum, and that's also right associated with the visual clear slot. So the rain is being evaporated away by this intruding downdraft. I'll show you a couple cross sections again, one just north of the tornado and hook, and one just through the south side of the tornado, essentially, the clear slot and the blob. So the north one, again, there's the hook echo. There it is. Hook echo here, the weak echo region is sinking and going away, and that's been noted for many years that the bounded weak echo region tends to collapse at the time of tornado formation. And still this is even more vivid than before. The inflow air welling up in the updraft, it's just keeping a good chunk of its momentum as it rises up in the updraft. When it gets up to mid-levels, it's encountering westerly winds, which are pretty typical of the storm's environment. So we have tremendous convergence of air right through the hook echo itself. And it's probably it's got some really complicated dynamics which I can share with you if you ask, but that's probably one reason we're seeing that spreading air right at the ground associated with the hook, is that strong convergence aloft in the hook itself. Picture time. Let's go to the mature phase of the tornado. Now this is 9 minutes after the tornado formed and a little bit 12 minutes before its death. And we have a photographer, Barry News, out to the east of the supercell looking west. There's the tornado. Here's the beaver's tail cloud. The updraft base spirals northward, eastward, southward, 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 southwestward, westward, northwestward. Over many, many miles now. In the course of 10 minutes or less, we've turned this into a great big cloud system. New beaver's tail forming here. Right in here in the original imagery, it's pretty clear to see a new slot forming, and that is the location of the new mesocyclone on the gust front. At this time, this mesocyclone on the gust front, according to airborne Doppler data, was stronger than the mesocyclone associated with the tornado. And that's simply an issue of resolution. We just didn't have enough samples cutting across here to fully resolve how strong the winds were. And in the case of this one, we had enough samples and it looked stronger. But that gives rise to this cloud map. Oh, now, everyone here knows who Ted Fujita was and how snazzy his graphics were. Tell me, really, did you ever do anything like this? Thank you. There's the big scale cloud map. Now we've gone back out in scale, but here's the tornado location over the diagonal highway. Cloud base wrapping west, north, east, south, southwest, and a total length here of maybe 15 miles now compared to the 3 or 4 miles early in the storm's life cycle. There's the frontal systems. Their position is known exactly from Dow radar data. There's the new developing mesocyclone and the location of that newly forming slot. This guy didn't go ahead and produce a tornado. And we're going to do some research to see if we can figure out why that is. I have some of my suspicions, but they're not good enough to really report. Photographs, this is confusing. Did I do this picture? That big wide angle one I just showed you is from Barry News, looking from south-southwest to west-northwest. If we look at a picture from right here, Cam 1, looking at the tornado off to the west, that's this. And you can see how this maps. This is just basically to give you an idea of how I came up with these cloud mappings. Tornado along this line, edge of the wall cloud along that line, base wrapping northward, eastward, and then back to the south. So that's where we get this part of the mapping. And then Ian Whitmire was to the southeast of the tornado, looking up the diagonal highway to the northwest. Big, different looking tornado now, just a big debris cloud with a debris curl. Edge of a wall cloud, all of this is cleared out of cloud, so that the lower cloud base comes out to the southwest and then way off in the distance off to the north and then back to the east. Right here to the immediate east of the tornado, no clouds, to a big depth. And looking up the highway from Bobby Eden's spot to the tornado to the north-northeast, white, very bright sunlit wall cloud from his viewpoint. The south and southwest side of the wall cloud is all sunlit. Big debris cloud in here. And then finally, probe 1, Bob Davies Jones, looking from just west of the tornado, inside the hook, obviously. There's kind of a white funnel embedded in a big gray debris cloud, and it's really hard to make out what's going on because he's just too darn close. This may go into a little too much depth, but let me try it anyway. Airborne data is what's the proper term? There's some slang terms. It's a mess to deal with. Thank you, Chuck. Let me just make a little editorial here. Chuck this morning showed an elephant with someone at each leg feeling this creature, trying to figure out what it was from what they could feel, and each one came up with a completely different idea. This is what happens when you do storm studies of this sort. We've got airborne data, mobile mesonet, cloud mapping, Dow radar data, soundings. If you just look at any one of those sensors, I promise you will come up with the wrong idea of what the storm's doing. I say that from my experience because every time I bring a new sensor into the mix, my old ideas go out the window and I get a whole new interpretation of what the storm's doing. So I say that to you as a word of warning. I'm not trying to criticize anyone else's work, but if you see studies of this sort, and they're only looking at one particular type of sensor and drawing some grandiose conclusions, take it with some grains of salt. Just from my experience, it takes a lot of time, a lot of hard work, and a lot of sensors to really start getting a feel for what the storms are doing. But anyway, that's that. That's my editorial for tonight. All you need to know here is that reds are rising, blues are sinking. Pinks are rising at 20, grays are sinking at 20 meters per second. Red's up 10 meters per second, blue down 10 meters per second. So in the lowest levels, at cloud base, 800 meters above the ground, that's actually a little above cloud base. There's my vortex. You can see how the swirl in the velocity vectors there, coming around the west through southwest, through southeast side of the vortex, as we can see it in airborne Doppler data, which is a really bad vision for these things. We see a downdraft wrapping around the tornado, and the tornado itself is embedded in an updraft. And then if we go higher in the atmosphere, up to 4,000 meters, we still see just the edges of the downdraft where if there's no rain there, the radar can't see it. I believe this downdraft extends out probably several kilometers from where we're seeing it and wraps around the south side of the vortex. The vortex itself is embedded in what is now a fairly much larger updraft at 4,000 meters. This sort of picture has been seen for many years in Doppler analyses. This isn't too novel. What I find interesting is the fact that in the updraft, the wind flow is very weak. It's like we have low-level momentum that's brought up in the updraft and gradually diluted to something weaker. And then aloft, the flow is diverting around both sides of this updraft. And this is where the hook is, in fact, the back edge of the hook where this flow tends to split and go around. That pattern is associated with anticyclonic vorticity and cyclonic. This is another feature that's been predicted for many years, that if you take this low-level horizontal vorticity, draw it up in an updraft, it gives rise to both signs of rotation straddling the updraft. What I find most interesting is that what goes on at this hook echo, like I showed you a minute ago, the inflow air comes up and encounters air with very much different velocities that is in the storm's environment. There's several things that could happen. That could force air to rise above it and sink below it, which is what you usually expect. But in this case, because of a peculiarity in the way we have dense air and warm, moist air adjacent to each other, the air not only rises and sinks when it comes together, but it also spews out laterally the other direction, which is what you're seeing here. The air is accelerating in both directions at the backside of the storm. And this air basically comes around and sinks in a cyclonic shaped downdraft right around the side of the tornado. Blah-de-blah-de-blah. Temperatures at 0106. Oh, there's temperature contrast. Where do they come from? Tornado, fronts, temperature, isotherms. Here's the hook. The tornado's right at the tip of the hook, a skinny little hook. The coolest air is right under the hook, approximately, less than 19 degrees C. Warmest air is just to the rear of the hook, a couple of miles, more than 22 C, and just to the south-southeast of the hook, reaching up to 23 degrees C. Much warmer air than we've ever seen in the life cycle of this storm so far. Basically, we've got downdrafts that are coming down wet and staying cold through evaporation, and also we're having downdrafts coming down without rain in them. They get within a certain distance of the ground and they start being heated, dry adiabatically or compressionally heated, and they get to the ground warm. Why is this important? Well, Chuck and Harold and others have said for quite a while that one failure mode of a supercell is that you get too much cold air in the rear flank downdraft, it goes spreading out and you can't have a tornado. I think we're seeing that here. The air isn't getting to the ground very cold at all. In fact, it's practically no different than the inflow air. And in fact, some of it's getting to the ground warm, which means that if it's ingested into the tornado, it can accelerate back up again. It's kind of like if you studied overshooting parcels. It might give rise to an overshooting top on a supercell. This is an overshooting downdraft that goes beyond its equilibrium level and starts getting hot and then bounces back up again. Okay. Winds, 9 minutes after tornado formation. Look how they spread away from where the hook is. See how they're going off to the storm-related winds going off to the southwest and off to the southeast, going off to the due south from the hook here, and then this part of the streamline pattern is from Dow radar data, which I'll show you in just a minute, but essentially coming off this streamline right here that goes spiraling around the tornado, the air is spreading in all directions. Why? Because there's a downdraft impinging on the ground right here, and the air is forced to spread away from it. What else does this tell us? If you want to know why a tornado's there, figure out where its rotation is coming from. It's not generating it through magic where it sits. It has to be coming through the tornado's inflow. the inflow to this tornado, I can show, is only about 15 meters deep. So I have to figure out, as a scientist studying the storm, how the rotation is getting into that air that's going through those bottom 15 meters and then erupting upwards in the tornado. So one of the questions I ask is, well, where's the air coming from? If you look at this and a bunch of analyses just like this, it looks like that air that feeds the tornado itself is coming in along the inside of the hook here, spreading away from the hook echo and into the tornado here at the south side. That we've seen, and that, oh, I've just got to show you this. This is just one of my favorite pictures. I'm going to try to wrap this up. Do I have at least 10 minutes left? Hot. All right. Cross-section time. Same time, tornado just crossing the road. Almost took out the good pasture fertilizer plant here. It raised some nice big white puffs of fertilizer into the air. Would have been an interesting scene if it had taken all of those chemicals airborne. Clear slot all the way around the tornado except the south side. Low cloud base spiraling out like I showed you, and there's the hook. Now let's look at a cross-section of airborne data through here. What I want to show you here is what does the hook look like back here. Well, you know Fujita, he liked to give names to things. He had this anteater echo. Well, I'm renaming it. Cumulonimbus pachydermis. That's the northern cross-section. There's that skinny little hook. There's the weak echo region as it's continuing to collapse toward the ground. Remember, it was 10 kilometers deep, not more than 10 minutes ago. Now it's just this deep. And again, we have velocities that look like inflow air rising up through the updraft here and encountering much stronger winds from the opposite direction, right where the hook resides. And that is, yeah, okay. I'm not going to tell you how I did this because it's going to waste 15 more minutes of my time telling you how. Suffice it to say, I came up with a very clever trick to come up with what the real wind is given radial velocities measured by a Doppler radar, using some constraints. My constraints are, I know what the mobile mesonet winds are here where I've got these radar indicated winds, and a little bit higher in the atmosphere I know what the airborne winds were, so I can use some clever assumptions and come up with my best guess at the real winds. When I put this through peer review, I'm in deep doo-doo, but I think it's a nice technique myself. I hope I can defend it. This is, in colors, are what we call divergence, which is the tendency of air to spread or contract horizontally. And the blues here indicate divergence. Here's my tornado, the spiraling cloud base, and its associated frontal systems. And this is where the hook is, where the center of the hook is this blue line. Notice all the way around the tornado, I've got strong divergence at the ground, about 500 meters out away from the center of the tornado. And then strong rising motion, strong convergence, which gives rise to rising motion, extending from the tornado out to the west, then off to the north along this front, and then wrapping off to the east along that front. Why is this important to me? Well, it tells me that downdraft is, and this goes along with the cloud mapping, downdraft has nearly engulfed this tornado. And if I want to know why the tornado's there, I better find out how that downdraft is essentially feeding rotation to the tornado. And remember earlier we had a pair of straddling the downdraft, we had a pair of vortices, one rotating cyclonically and the other anticyclonically. As time goes on, that pattern persists, but the anticyclonic part gets sprung out around the tornado. And the tornado itself obviously is a cyclonic vortex. So this is what we call, this is the vorticity of that same wind field right at the ground. Lots of blues indicating negative vertical velocity, vorticity, negative vertical vorticity all around the tornado. And of course, it itself is a center of cyclonic rotation. The reason that's important to me is I think it gives us a big hint as to why the tornado's there, which I'll summarize here in just a second. One more fancy schmancy picture. I'm exploring the near field of the tornado. In other words, going from the tornado out for maybe 1,000 meters. That region is critically important because it's going to tell us why the tornado is there. These yellowish, greenish, pinkish colored lines are reflectivity from the Dow radars. This is in the plane of the photograph at the distance of the tornado. So this little bowl-shaped hatched reflectivity area here, more than 30 dBz. What is it? If you look where the maximum is, it's right at the edge of the debris. So this large reflectivity is where the tornado has centrifuged out the biggest chunks of stuff. Big chunks give back a lot of power to the radar. So we see the highest radar returns right there at the edge of that debris where the stuff gets thrown out the furthest. And this other little feature is the hook echo itself. We wouldn't see it with our eyes. They're probably just a very few very large drops in there, not enough for you to ever detect with your eyes, but the radar can see it hanging down here just to the south of the tornado, kind of spreading when it gets near the ground. Up and down motion, sinking at 20 meters per second here at the south edge of the wall cloud, 10 meters per second. It's not well resolved. This may be the tornado itself, but I've got strong rising motion right here, and then again on the other side of the tornation. Our nation, man. Sinking, whatever that was I was saying, I don't know. I don't want to dwell on it, but it seems from what I've seen so far that this tornado eventually got engulfed by some cooler air that the hook itself was generating. Not much cooler, maybe a couple degrees C than when the tornado formed. And when that happened, the tornado quickly shrunk and stretched and turned into a rope and dissipated. Which leads us to wonder if it maybe isn't cool air that kills tornadoes off, when the air coming down in the downdraft just gets too cold for the air to effectively be lifted in the tornado. Another tornadic storm. I'm a liar. I'm not a good liar. This is a storm looking on Dow radar, hook echo, a cyclonic flare coming out. On the tip of that, a nice little cyclonic whirl and an anticyclonic wind, both of TBS strength, 300 meters above the ground, no tornado. This is a problem. Because this in every other respect that we've seen, this looks like a tornadic supercell. We haven't dug into it too far yet. But even down to just 300 meters above the ground, it looks like this storm is for sure going to produce a tornado, but it doesn't. This is one of our null cases. We're going to really dig into it to try to find out why. We have a fear, at least in terms of operational meteorology, that the reason why it didn't produce a tornado is just maybe there was perhaps just this shallow layer of cold air right at the ground that couldn't be penetrated by the rear flank downdraft all the way to the surface. And that was the difference between tornado and no tornado. If that's the case, we've got a major problem, as you operational folks realize. If you put out a whole bunch of cars with geek-mobile outfits on them, you'll know if that air's too cold. But there's just no other way of knowing. If that's true, if a little shallow layer of cold air can kill your chances, it's going to be awfully hard to know operationally whether that layer is there or not.
What was the date of that last one, Eric?
8 June, Beaver County, 8 June 95. This is now moving into the summary. Doesn't mean I'll be finished anytime in the next hour, but summary anyway. What do observations tell us? This isn't just Dimmitt. Jerry Strzok and I went through all the tornado literature for the last 30 or 40 years and tried to come up with common threads. I feel it's very important to do that instead of just focusing on differences between storms. See, even despite all these differences, are there some common physical threads? Some things you come up with is that significant tornadoes are associated with supercells. No does, please. I'll tell you what I mean by that in a minute. It's possible that the process we saw at Dimmitt and some other storms is this. A supercell comes into some of this air that's rich in horizontal vorticity or helicity. And when it starts drawing that up into the updraft, the rotation picks up. When you increase rotation in a storm, the pressure falls, and a consequence of that, or something that happens in concert with these other processes, is that inflow increases. If you start sucking harder in a supercell, it tightens up this horizontal rotation of the air as it's going in, and that increases the spin even further. So it's a feedback process that can really crank the rotation up quickly. We see that a tornado cyclone, or the smaller scale vortex, builds upward and downward. In this storm and a number of others, there's a downdraft at the back of the updraft, and straddling that is anticyclonic and cyclonic vorticity. In fact, sometimes there's so much anticyclonic vorticity that the hook comes out and gets this anticyclonic flare on the end before it ever wraps up with the cyclonic shape. And in all the observations, negative vertical vorticity persists throughout the tornado life cycle. Papers here. By the way, this is a good reminder to me. I'm going to post this talk on the web at this site when I get back. And it'll be on that main page there, it'll be under a little topic called Talks. What do I mean by a supercell? Oh, heavens, why am I saying this? I'm going to get myself in trouble. Chuck, please leave the room. Some things in vortex are telling us that maybe we need to rethink some of our ideas about tornadic supercells. And so in terms of what a tornadic supercell is, let's talk about a storm that has an updraft strong enough to tilt and stretch low-level horizontal vorticity and turn it into a mesocyclone down there in the lower part of the updraft. Not every storm updraft is strong enough to do that, and not every environment has enough horizontal vorticity to feed this process. But what I'm saying in this slide is that we've had this picture in the back of our minds for for a couple of decades anyway, of this nice big sculpted rotating storm marching through the plains, and the rotation gets a little bit stronger, and the storm gets a little bit prettier, and after a couple of hours you get a wall cloud, and then a tornado forms, and that's how it works. I don't believe tornadogenesis is that way. I believe tornadogenesis is a very fast process that has to do with a whole lot of low-level tilting and stretching. And we need to look for storms that are capable of doing that, not just these beautiful beasties that go marching along for hours. Maybe it's even a squall line encountering a boundary. That's the point I'm trying to make here. We also need to talk about storms that can survive long enough to produce a tornado. Now that rules out a lot of storms. A lot of storms develop so much precipitation in their updraft that the downdraft comes crashing to the ground and spreads out in all directions, and this couldn't go on long enough to reach tornado formation. And there's my editorial comment right down there. It doesn't have to be a long-lived, steady-looking storm by any stretch of the imagination. Oh, gosh. Now I'm going to put something up that I don't believe. But it's going to be a good illustration, I think. I want to give you an idea of where it looks like tornadoes are coming from. And this will serve as an adequate illustration, although the details of this I'm beginning to feel are probably wrong. Hasn't made it to press. Should I withdraw? Yeah, who cares? Let's talk about it. This paint can is an updraft. And in the middle, the air is going up the fastest. And at the outside, the air isn't going up at all. It's just sitting still. So if you can picture a paddle wheel in there, that gives rise to spin like this. Now, at the same time, the whole updraft is rotating like a top, which gives rise to vertical vorticity. And if you add those two together, you get vorticity lines. That's lines that connect, that show where the vorticity vector is pointing everywhere. It's parallel to them everywhere. That I know is going to go way over a lot of people's head, but just picture a rotating updraft. That's all this is. It's a rotating updraft, and that's what the vorticity looks like. Now, if we start the air sinking on the back side of that for whatever reason, we take those vortex lines, we start dragging them toward the ground. Here, we drag them a little further, and then we get them all the way to the ground. Initially, that gives us a region in the updraft where the vertical vorticity gets to be